here we're given a vector field, and the question that we had is whether that's a gradient vector field, meaning that it's a gradient of some potential function. And it's asking us to find out what that potential function is that would produce that. So in other words, we are looking for some function xy where if you differentiate by x and differentiate by y, that's what gradient is, right? Differentiate by x, differentiate by y, that's what gradient is. And I want this to be equal to 2x minus 6y and negative 6x plus 2y. Okay. So here's what we have. F, if you differentiate by x, it's 2x minus 6y. And f, if you differentiate by y, it should be negative 6x plus 2y. Okay. Now, the first test is the following fact. We've learned some time ago that if you take a function and differentiate by x and then differentiate by y, and if you take a function and differentiate by y first and then differentiate by x, they're equal, right? So the order of derivative doesn't matter. You end up with the same answer. So the first way to test whether you may have such an f or not is that if these two functions came from a single f, it better be that if I take this one and differentiate by y, if I take this one and differentiate by x, it better be that they should be equal. If they're not equal, then there's no way it's derived from a single function, right? So what we do is we take this and differentiate by y. What do you get if you differentiate by y? Derivative with respect to y is 0, and differentiate by y gives you a negative 6. Okay. What about this one if I differentiate by y? No, by x. This is already differentiated by y, so if you differentiate by x, it gives you, again, negative 6. And they're exactly same, right? Okay. So that's if these two things match exactly, and then such a vector field is called an exact vector field. So it's known that gradient vector fields are exactly the exact vector fields. Well, there are some more complications when the function has a singularity. So if you have like 1 over x or something, then that causes things to not work. But that's a very theoretical kind of question that we won't address in this class. Although, you know what, like if you think about the force between two charged particles, which is like k times q over r squared. Like this r squared is really x squared plus y squared, so it does have a singularity at 0. So, and this vector field comes from, actually a minus. This vector field comes from this potential function in physics too, right? So, I mean, in physics, you do end up with some functions that have singularities, but we'll just conveniently ignore them. And for this class, anytime this happens, it must have a potential. That's how we're going to simplify things. Okay? But there are some more complicated rules when your function is not defined in a single point, and then yeah, there's some more stories there, but we'll not go there. Okay. All right, so we found it to be exact. So thus, f is an exact vector field. Okay. And there's some mathematical complicated theorem which says that if it's an exact vector field, then you can find the potential function. All right? So that part is done. We know that such a field, a vector field exists. And often, this test is going to be a quick one if it turns out not to be exact. If it's not exact, then we don't even have to try. Then it's not, that's it, that's over, okay? But here, it is exact, so we now have to pursue the potential function. How do we do that? Well, let's undo the derivative, okay? So let's undo the derivative, which means f is going to be taking this 2x minus 6y, you should be integrating by x, right? Now, we haven't discussed integration much, but this interval is really a partial integration, meaning that you treat y as a constant, okay? So if you integrate this, you get x squared minus 6xy. Is that good? Okay. However, there's a catch. Since we're considering y as a constant, we can't just put plus c, because c could be something that has y in it. So instead of putting a c, we should really be writing down g of y. You get what I'm saying? Okay, so you've been yelled at. Well, I guess you guys had good professor who didn't yell, but yeah, I would yell in Calc 2, like, you forgot plus c, right? Yeah, over and over again until everyone got that. Yeah. So you've been instructed to always put plus c, but here it's not plus c anymore, it's plus a function of y, because it's a partial integration. Okay? So that's one point to think about. And now let's do the same thing for the other guy. For this one, we should integrate by?
Y.
It's differentiated by y, so to undo the derivative, we have to integrate by y. So negative 6x plus 2y dy. And that gives you negative 6xy plus just y squared plus
G of x.
yeah, but we don't want to use the same g, so let's say h of x. Okay. So it's a partial integration, so the constant could be a function of x. Okay, how are you confused? Be honest, if you're confused, raise your hand. Okay, if you're confused, you can do the following. If you took this and let's say this is your f. What's fx? Do a partial with respect to x. This gives you 2x, right? This gives you negative 6y, right? So you get 2x minus 6y, and then what happens if you differentiate this by x? 0. So you get exactly this, which is what you started with, right? Isn't that right?
Mm-hmm.
So how do you verify an integral? You differentiate, and if it matches with the original thing that you integrated, that means it's correct, right? So it's correct. Well, this is indeed correct. You need a g of y. Same thing here. It's h of x. Okay. Now you have two different descriptions of the same function. Here, this f and this f these two f's are the same thing, right? And you have two different descriptions of the same function. And it's like, let's say you're a detective, right? And somebody stole a Mercedes or something. And you're in the neighborhood trying to ask, like, did you see any suspicious person in this neighborhood, right? And this person one will say, oh yeah, that person had a Yankees cap on and blah, blah, blah. Okay. Other person will say, oh, it was a tall guy with sunglasses on or something, right? And then what's your role? You have different witnesses describing different parts of that. Some will overlap, some won't, and you have to harmonize everything to come up with a single coherent description of this guy who stole the Mercedes, right? That's how you do detective work. Okay? That's exactly what you have to do here, right? So what's common in these two descriptions?
Negative 6x.
Negative 6xy is the common one, right? And this guy says, well, the function had the negative 6xy, it had x squared, and there was some function of y there, but I don't know what it was. I can't remember, okay? The second guy says, well, the function had negative 6xy, and there was plus y squared, and there was some function of x that I don't remember which one it was, okay? And then if you're the detective trying to harmonize the two different witness accounts, what do? What's your final answer? Your function must be?
The h of x is the x squared.
Yeah, this must be x squared, and this must be
Y
y squared, right? So you should just say negative 6xy plus y squared plus x squared. That's it.
But couldn't there be a constant?
That's true too. Okay. That's could be out of it. That's the general. In many cases, you don't need plus c because you're going to use this for something else. And in many cases, it doesn't say the potential function. They'll say a potential function. That's the correct one because there are many different answers with different c. Okay, yeah. I was going to talk about it, but you beat me to it. That's very good. Okay. All right. So that would be the potential function. Is that good? Yeah, so to summarize, here's what's happening. Let's say vector f is m comma n. So m is a function of x and y, and n is a function of x and y. Then if m differentiated by y is equal to n differentiated by x, right? We say f is exact. Okay? If that's true, we say f is exact. And if it's exact, then because we're thinking of this as derivative with respect to x of some function f, and you're thinking of this as derivative with respect to y of some function f. So I'm thinking of this one as f differentiated by x and f differentiated by y. Right? You just have to undo those derivatives. You take this one integrate by x, you take this one integrate by y, and then you have to harmonize the two accounts. But when you do the integrals, don't forget to put those functions there, okay? That's it.